This is Unit 3, Topic B. We're going to be looking at what derivatives tell us about graphs. Our first section here is talking about relative extrema, the maximums and minimums. And in order to determine those using calculus, we'll use what we call the first derivative test. This is actually something we've already been working toward a little bit because I think you've noticed some patterns that are going to help out a lot. First of all, let's get this part of the way. We've got some very mathy definitions of the relative maximum and the relative minimum. Relative maximum says if there's an open interval containing our point C such that the y value, f of c, is greater than all of the other y values, f of x, within that interval, then we have a relative maximum. And of course, if the y values are smaller than all the other y values, then we have a relative minimum. So that's just all of that written out in a very mathematical way. Realistically, as you look at this graph, I see two relative maxima. There's one here, and there's one here. I also see two relative minima. There would be one here. It's lower than all the other points close by. And one here. Notice that for the relative maximums, it's not that they are the highest point anywhere on the graph. They're just the highest point kind of in their own little neighborhood. That's what these intervals I are about. So this is the maximum for everything close by. This is the maximum for everything kind of close by. It's not the biggest point in the whole graph. The graph keeps going up forever, in fact. But in its neighborhood, it's the highest point, the top of a hill. Similarly, those relative minimums are the lowest points in their own neighborhood. Think of them kind of like the bottom of a valley. All right, well, we said that we were going to be able to use derivatives to tell us where these relative maximum and relative minimum points are. And in order to do that, take a look at these 4 points we have marked and think about what the derivative would be at those points. In 3 cases, I'm going to contend that it's somewhat obvious. There would be horizontal tangent lines at all 3 of those points, right? So with a horizontal tangent line, the slope and therefore the derivative would be 0. So, if the point C, f of c, is a relative maximum or relative minimum, then one possibility is that f prime of c is equal to 0. But there's also another possibility. Let's look at this last one. What would you tell me about the derivative at that point? Well, this is one of those where it depends on which direction you're approaching from, right? As you come in from the left, it looks like the derivative is a positive value. But as you come in from the right, the slope is looking negative. So when the two sides don't match up, we say that right at that point, the derivative doesn't exist. So the other possibility is that f prime of c doesn't exist or is undefined. That's how we're going to identify points as sort of candidates to be a maximum or a minimum, is by looking for points that we're going to call critical values, where the derivative is 0 or where the derivative fails to exist. That leads me to my next question. Suppose that we know that a derivative is either 0 or fails to exist. Does it necessarily follow that our point is either a relative max or a relative min? I'm actually going to say no to that one. Here's a perfect example right here. Right at that point, the tangent line would be horizontal, right? Coming in from the left, you'd have a tangent line horizontal that way. Coming in from the right, horizontal this way. So even though at this point, which happens to be x equals 4, we have a horizontal tangent line or a slope of 0, it's neither a maximum nor a minimum point on our graph. So the answer here is going to be no. It is possible for f prime to be 0 or undefined, but not be a maximum or a minimum. In our graph, f prime of 4 would be equal to 0 because the slope, as we saw, was 0. But there's no max or min at the point where x is 4. So, how are we going to deal with this? We know that if the derivative is 0 or undefined, we have sort of like a candidate. It's a potential max or min, but it's possible that it won't turn out to be one. Here's what we're going to need to look at. We're going to need to look at the behavior on each side of our potential maximum or minimum. If we have a maximum, notice that to the left side of the maximum, we're going uphill. All of our derivatives would be positive numbers. All of our slopes are positives. So all the f primes would be positives. And on the right side of the maximum, we'd be going downhill. So our slopes or our derivatives here, whoops, I'm sorry, I wrote that wrong. All of our slopes would be positive. That would be greater than 0. And here when we're going downhill, our slopes or derivatives would be negative. They would be less than 0. So if our derivative changes from positive to negative, we have a maximum. On the other hand, if it changes from negative to positive, we have a minimum. Now what happened here? Well, let's see. Downhill, so we had a negative slope from the left, and it's still down here. So we still have a negative slope to the right. Notice that our derivative didn't change from positive to negative or vice versa, which is what's going to tell me that I don't have a maximum or a minimum at that point. So let's summarize all of that on the next page. We're going to call this our first derivative test for relative extrema. Extrema is just a one-word name for maximums and minimums put together. First of all, x equals c again is a critical value if the derivative there is 0 or undefined. Think of it as a candidate to become a max or a min, but we don't know yet. X equals c is going to be a relative maximum, right? Let's just think about this for a moment. If the derivative is positive on the left side, uphill, negative on the right side, downhill. We're going to create a little diagram where we put our critical value c on a number line, and then we'll just test some points on either side of it, very much like what you did with limits, not surprisingly, right, because the derivative really is just a limit, remember. And if we get positive values for f prime on this side and negative values for f prime on that side, then we know that right at c we have a maximum. Oftentimes when we make these diagrams, we'll even show that by saying, okay, positive derivative, that would be uphill, negative derivative, that would be downhill, and then our diagram even kind of shows us how we're going to end up with a maximum in there. Our critical value, x equals c, then would be a relative minimum. if the left side is downhill, so f prime would be negative on that left side, and then uphill, so f prime would be positive on this side. And again, we'll typically do that as a little diagram. We put our critical value c on the number line, and if we have a first derivative that's negative on this side and positive on that side, so downhill or decreasing, uphill or increasing, and we have a minimum at c. If our first derivative doesn't change signs, if it's positive, positive, or negative, negative, then our critical value doesn't turn out to be a local maximum or a minimum at all. All right, so let's take a look at this example. We've got this function, it's a cubic polynomial, and I would like to find and classify. Classify means just say if it's a max or a min. All of the relative extrema, and we'll also list our intervals where the graph is increasing and decreasing. So first of all, I want to find those critical values. F prime in this case would be 3x squared minus 6x minus 24. And clearly that's never undefined, so all I have to really worry about is where it's equal to 0. Looks like 3 times x minus 4 times x plus 2. So our critical values are going to be x equals 4 and x equals negative 2. Now I'm going to test those critical values by placing them on a number line. And I'm going to kind of imagine that this partitions my number line into sections. And I want to know if the derivative is 0 at both of these places, then what's true about the derivative in each section of my number line? In order to determine that, I'm just going to pick a test value and plug it in. Now at this point it's up to you. If you're pretty good with plugging things in your head, you might just do it that way. If you don't love plugging in numbers in your head, you are welcome to use the calculator. We're going to plug into the derivative. So this was my derivative right here, or I could use the factored form, it really doesn't matter. So I'm going to put in 3x squared. Oops. I don't know why I put that in y2. Let's try that again. 3x squared minus 6x minus 24. That's my derivative function. And let's first of all pick a test value in this last interval on the left. Anything less than negative 2 would be fine. I'm going to go ahead and try, say, negative 3. Clearly my derivative is positive, and that's all I care about. So it's positive there. We'll pick anything between negative 2 and 4. How about 0? At 0, my derivative is negative. Again, I don't really care the actual value, just positive or negative. And then we'll pick a number bigger than 4. How about 6? At 6, that derivative was positive again. So what does this tell me? Well, it tells me that the function was increasing, going up here, decreasing downhill with a negative slope there, and then increasing with a positive slope here. So if you just kind of look at the shape of that, we can see that we have to have a maximum at negative 2, and then down to up, we have to have a minimum at 4. So I will start with that information. We can get the actual point just by getting the y value. I'll plug -2 back into the original function. I'll do that in just a minute. And then a minimum at 4 comma whatever the y value is. I'm done with the derivative, so I could plug in my original function now. And at -2, the original y value was 38. And at 4, the original y value would have been -70. So I have one maximum and one minimum. As far as the intervals of increase and decrease, intervals of increase, let's see, we're increasing or going uphill from -infinity until we get to -2. And again, starting here, we're increasing from 4 to infinity. The intervals of decrease, and I think there's only one in this case, where the graph is going downhill, happen between -2 and 4. So notice that when you're giving intervals of increase and decrease, you are giving intervals of x values. Saying from this x value to that x value, the graph is increasing or going up, and so on. All right, let's pause there, and we'll come back and talk about what the second derivative tells us in the next video.